horizontal position and vertical position. So two numbers give you enough information to identify the location of a given unique point on the plane. There are many other ways to describe position. One of them is polar, and instead of x and y, you use anybody want to guess? It's up there on the board. R and theta. What is R? Can someone clearly tell me what R is? The R value of a point is what, Tomas?
It's like the distance from the origin.
So it is the distance from the origin, isn't it? Yeah. The distance the point is from the origin. Not like, it is. It is. Excellent. What's theta? What's theta?
It's like
Stop saying like. Stop saying like.
The angle it makes.
Which angle? The angle what makes?
The x-axis.
What? Stop using pronouns.
The point.
The point? Points can't make an angle.
But if you draw like a line.
Stop saying like.
I'm sorry.
I'm glad this is on tape, by the way. Yeah, go on. Go.
If you draw a line.
Not a line. You don't have to draw a line.
Well, it would be a ray.
A ray. There you go.
In the x direction to the right, the positive x direction from the origin.
Yep. And
you draw a line.
Ray. I like ray. From the origin.
Ray. Okay, so a ray from the origin
through the
point.
Yep.
You find the angle between those two.
Which direction? You need a direction. Which direction are you going in?
Counter.
So it's the angle formed in the counterclockwise direction between the ray on the positive x-axis and the ray formed from the origin to the point in question.
Yes.
There it is. There's a lot of words you have to use. You can say it different ways, but you have to be specific. Like you can't create an angle between a point and a point. You need an angle between a ray and a ray. You can say different things though. The idea here though is that in this case, there's the point U. That point U in Cartesian land is labeled as what? 3, 4. Yay, exciting. If you wanted to describe it in polar coordinates, you would need the R value and you would need the theta value. Sometimes these are nice because they are wonderful trig values that you've memorized, and sometimes they are not. Get over it, right? Tangent's really common because if you have x and y coordinates, you'll have the x and y, you can find tangent really easily. You won't need that hypotenuse. So what is that theta value again? Well, tan inverse of 4/3. Wonderful. What about the distance? How far is that distance? What's the R value?
5.
Why do you know it's 5? Well, it's a what triangle?
3, 4, 5.
It's a 3, 4, 5 triangle. Or sometimes the triangle's nice. Yes. Anybody remember off the top of their head about what that angle measure is? You've seen it so many times. It's like what?
I definitely know this.
Anybody know?
37 degrees?
No, it's more than 53.14, something like that. Something like that. You see it so much that it happens. Okay, so here's the thing. What you notice are a few relationships. The first is that x is equal to r cosine theta. If you actually draw in the triangle here, if you draw in this triangle, if you have, this is theta, here's x, and here's y. How do you know x is r cosine theta? Well, what is cosine theta? Cosine is, what's the definition of cosine? Adjacent over what? Hypotenuse. In this case, what is the adjacent? R, and what's the adjacent is what? X. And what's the hypotenuse? R. So then you cross multiply and you get x is equal to r cosine theta. Similarly, what does y equal? R sine theta. You've seen things like this before. This is not new. And then what is r going to be equal to? Oh, the square root of x squared plus y squared. And tangent of theta is equal to y over x where x doesn't equal 0. Exciting. These are things you have seen before. They need to be interchangeable in your mind though. This needs to be interchangeable with that. This needs to be interchangeable with that. Fantastic. So you can go back and forth here, and sometimes you'll have to know what these are. So give Cartesian coordinates for the points with polar coordinates. So what does this mean? What does this mean? I left some of them in there. So these are polar coordinates, 5, 0. What does that mean? What does 5, 0 mean in polar land? What does that mean?
Is it just 5?
What does that mean? Yeah, where is it? Describe it with.
So it's 5 units
away from the
origin,
and it's
on the positive
x-axis because it's forming an angle measure of
0.
That's angle and distance, exactly. So on this first one, what's Q going to be actually in Cartesian coordinates? 5, 0, right? Over 5 up 0. So can they be this? Can you actually write them? Some points are the same. Yeah, anything on the x-axis is going to be the same, right? What about 5 pi? What does that mean? That's the angle, right? From the positive x-axis. So what point is this going to be? It's a distance of 5 away. So what's the Cartesian coordinate going to be? Negative 5, 0. Exactly. It's going to be negative 5, 0. Now those are nice because they are on axes. Yeah. Does this get a little bit more fun if I said like 3 pi over 2? Yeah, sure. It gets a little bit more, but not much. You just have to be careful. You just have to be careful. Okay, so if you're just careful with this, I'm giving you like the preview of everything right here, just by preview. Give polar coordinates for the Cartesian given by u equals 3, 4. Well, we just looked at that, right? You need r and theta. What's the r value? 5. And then you would say tan inverse of what? 4 over 3. Now, if this was a non-calculator section, you would stop right there. I do not want you to write a decimal for that. If it was a calculator section, you could still stop right there or write to 3 decimal places. And in this case, it's one of the few places where degree might be okay. But in general, unless the AP calculus test tells you otherwise, what do you stay in? Radians. Stay in radians, please. What about this one? So this is Cartesian 0, negative 5. So where is that? 0, negative 5 is like right about there. So what's the distance from the origin? Distance. The distance from the origin is 5, right? So the r value is 5. But what's this angle measure? 3 pi over 2. 3 pi over 2. 3 pi over 2, right? We good with that? 3 pi over 2? So understanding what this means is key. And instead of getting a nice grid like the background of this sheet or this projection, you end up with grids that look like that. So that would be polar graph paper right there. That's polar graph paper. It helps you find specific points on the polar plane. It's pretty cool. You can generate this stuff online, paste it into your work. It's kind of cool. So let's describe a few of these things. Why don't you stand up, everybody? Let's just stand up. Let's look at Let's look at A here. Describe in words the graph of y equals 1 in Cartesian coordinates and the equation r equals 1 in polar coordinates. So y equals 1, what is that? What is that in? It's a horizontal. It's just a horizontal line, right? It's just horizontal line. Yay, exciting. But what does r equal 1 in polar coordinates? Oh, I'm still frozen, sorry. What does r equal 1 in polar coordinates? If r is the same, is theta in there? So that's for all theta values. So what is that? What circle is that? It's the unit circle, right? It is the unit circle. So what's kind of cool is that sometimes polar functions can be simpler than their Cartesian equivalent. We think polar is more complicated. Well, how do you write a unit circle in Cartesian coordinates? Yeah, x squared plus y squared equals 1. That is more complicated than just r equals 1. Kind of cool. Write the equation r equal 1 in Cartesian coordinates. Oh, we just did. Right there. Write the equation y equals 1 in polar coordinates. That's the fun one. Write the equation y equals 1 in polar coordinates. So the distance from the origin is changing, right? So the r value is the same? No, the r value is different. What about the theta value? That's different too, right? So let's just what does that horizontal line look like? What does that horizontal line look like? Well, it's y equals 1, right? It's y equals 1. All these points, you just want these points, right? You just want those points? So how would you do that? What's the commonality between all of those?
So cosine of theta is 1 over...
Oh, so you want to do cosine?
No,
okay.
No.
We could?
No. I get that doesn't work.
So if this point right here, let's look at that point right there, and it's y equal 1 right there. Let's say we have theta right there, and we have y, and we have what? X right there. Okay, so what do we know here? We know that, what do we know? We know that y is equal to what? 1. We know that x squared plus y, x squared plus y squared has to equal what? That's not good. R, right? Does that help? There's r, right? X squared plus y squared is equal to what? R squared, but what does y always equal? 1. So x squared plus 1 is equal to what?
R squared.
R squared? So we know, oh, that's cool. We have r squared is equal to x squared plus 1.
R is equal to 1.
So what does r equal?
Square root of x squared plus 1.
Plus or minus. We want plus, right? Because that's to be positive. We want to keep the principal root.
Oh, yeah.
We like this, okay. But we want in terms of r and theta, right? What do we know x is equal to? What is it? R cosine theta. So what do we have here? X is equal to r cosine theta. So what do we have here? R is equal to the square root of what? Cosine theta squared what? Plus 1. Now take out your calculator, everybody. Take it out. You can sit down now. Sit down. Let's So go to pole. There we go. So then, oh, like it's r equals, right? So what did we have there? The square root of, what was it? R squared cosine squared plus 1? Sure. It's going to be careful about that. So what was it? So it's going to be... Oh, do we have an issue here?
Wait, yeah.
Oh, we have an issue here. We can't plug it in. We're limited here. So is there another way we can do this? Oh, no. Is there anything we can do? Not technically incorrect, but what do we know for a relationship? We know x is equal to r cosine theta, right? But what does y also equal? R sine theta. But what does y equal? What does it tell you? 1. So you have 1 is equal to what? Oh, it's still frozen. Sorry. So we didn't like this. Not incorrect, but it just didn't get us anywhere. But now what do we have here? 1 is equal to what? So what does r equal? 1 over sine theta. Is that easier to plug into your calculator? Yes. Yeah, let's see what happens here. So if we plug that in, if I can clear the whole thing, 1 divided by sine theta. Zoom standard. Hey, is that a horizontal line? Woo! Did it work?
Yeah.
Cool. A lot of working in polar, like parametric, sometimes you run into a wall, you renegotiate, and then all of a sudden you find a really clear path really easily. You will spend time doing algebra that will run you into walls. That is totally fine. Were you able to graph this successfully on your calculator? Raise your hand if you were able to graph this. Some of you don't have a calculator, so it might be hard. I know. You got it? Did it work? We're not doing that. We're doing this right here. Woo. Okay, so how are you feeling about understanding polar coordinates themselves? How are you feeling about understanding polar coordinates? What are the relationships? X is equal to? Cosine theta. Y is equal to? R sine theta. And what does theta equal? Tan inverse of? Y over X. Yeah. So and then you know that, what does R squared equal? X squared plus Y squared. You will bounce around between all of these constantly. But here's the topic that we really need to know. Here's the topic that we really need to know. Get up and find a place on the board, everybody. Let's draw some flowers, because people like flowers, right? Bring your calculator with you. Bring your calculator with you.
Yeah, something long. Can you pass me one of the markers?
Why don't you use that board over there. Use the left space over there. Okay, here we go. Draw me those two right there. Draw me those two. Did you get something that looks like these two? Oh, you can't see it again. These two?
Something like that.
Yeah. You will need to know how to graph. I don't know what that blob is over there.
Yeah,
something like that. What is this? It's like
I
a
really-
Rorschach test? Did you?
I really
You're like, it's like one of those like anti-see the picture things.
Yeah.
Here's the thing. On the AP test, on the non-calculator section, you will not have to know how to graph roses by hand. You will know how to graph roses by hand. Things that are of this form right here. These two right here. You need to know how to graph those by hand. So I'm going to leave that to you to just know that you need to study those. How many petals, how many times. What does like the n theta do? That kind of thing. You have to know what happens. Yeah, some speed. And what does the A do?
Does it have that in our book?
Yeah, something like that. How many petals, that kind of thing. I mean, like what's going on here? How many petals do you see there?
4.
How many petals do you see there?
3.
Yeah, where's?
For cosine?
Yeah, you have to look it up. You have to look it up. This is just something you have to look up and know. I'm not going to go through the list now because it's just me putting a list up and it's literally memorizing like 5 things. You just have to know how to do it.
For this class or just for the AP?
Yes. Okay, so let's move on here. Was that clear enough for you?
Was that a yes?
Can someone explain the logic of answering yes to an or question? When I answer yes to an or question, what does that mean? Both of them, yes. Means both. Okay, so this is what's really important here for this section here. What shape is this on the left? What is that shape? It's a circle, right? What's this called?
A sector.
A sector. It's called the sector of a circle, right? If you want the area of a whole circle, what is that? Pi r squared. So pi r squared right there represents the area of the whole circle, right? So if you want the area of just a sector, you want pi r squared, but you want the percentage of just that theta value, right? All the way around is how many radians? 2 pi. So if theta is in radians, what fraction of the circle are you dealing with? Theta over 2 pi. So this is the fraction of the circle you want times the whole area. So if you multiply these two things together, what do you end up with? The area of the, what's this called again?
Sector.
What is this then?
Area of the sector.
Area of the sector. You should have seen this before. The area of a sector is 1/2 r squared theta. Is that vaguely familiar to you?
Yes.
Okay, so the idea is if you want the area of a sector and you know theta in radians and you know r, can you find the area of that sector? Yes. Okay. This right here is a limacon. Sorry, limacon with that really cool C thing, limacon on it. Is it kind of a circle?
No, I mean like.
Yeah, it's kind of a circle, right? It's kind of a circle. It's kind of a circle. It's also kind of a circle that polar graphs are going to be defined by an arc movement around a circle. Because instead of scanning from left to right, you remember when you graph things at parabola, you graph from what? Left to right. When you graph a line, you're usually graphing from left to right. Now what are you graphing? You're graphing around the theta values, right? Is the r value staying the same?
No.
No, if the r value was staying the same, what would we have? It'd be a circle. We do not have constant r values. R values are going to change, right? But if we take really, really, really small theta values, how close together are the r values?
Yeah.
Speak so that humans can hear you.
Very close.
Very close together, right? So if theta is really small. Here's r1 and here's r2. How close are they going to be together? As we make theta infinitely small, r1 and r2 will get what? Infinitely small. So if I wanted to chop this up into sectors, could I chop this up into tons of sectors?
Yeah.
Chop up into a lot of them. If I add up the area of all the sectors, I get an estimate for the area of the limacon, right? It's an estimate because R1 doesn't equal R2. But as I chop it up into more and more pieces, does this logic sound familiar, everybody?
Yeah.
So instead of adding together an infinite number of rectangles, we're adding together an infinite number of sectors. And instead of integrating from A to B, scanning from left to right, we're going to scan from the starting theta value to the ending theta value. So on this one, for example, what would be the starting integration value? Maybe 0. And then you go all the way around and get back to, not back to 0, how many? 2 pi, right? Side note, could you integrate it from like here all the way around?
Sure.
Absolutely. Make it easier on yourself. 0 all the way to 2 pi. Do you notice symmetry in this?
Yeah.
So you could actually do 2 times what integral? 0 to what? 0 to pi. So we're not scanning from left to right. We're now scanning from a starting value here all the way around. And this is the area of one sector. This is the area of one sector. So what does the formula for the area of something in polar going to look like? It's going to look like this. Really, really straightforward. Area region is 1/2 the integral from alpha to beta of f theta squared d theta. What is f of theta? F of theta is r, written in terms of what? Theta. So this is 1/2 r squared theta. Does that look familiar? But the theta is getting chopped into infinitely small bits. Generally speaking, what's going to be the hardest number to find out here? It's similar to integrating the arc length on alpha and beta. Exactly. Alpha and beta. Remember when we did parametric arc length? You had to make sure it didn't overlap itself. Are these going to overlap themselves all the time?
Yeah.
Like when you draw those flowers, it's going to go over itself as many times as you want if you keep theta going, right? In this case, it's just going to be very, very tricky sometimes to find alpha and beta. Sometimes the question gives it to you, and that's awesome. There was another caveat that I gave you for arc length and parametric. Do you remember what it was? If you have your calculator, use it. Remember how sometimes you would generate arc length integrals in parametric and they'd be like impossible to integrate by hand? Is that going to happen here?
Yeah.
Yes, it's going to happen here. So what are you going to use a lot to find the actual numeric value of the arc length? Your calculator. Your calculator. The AP test is also going to give you questions frequently that say, set up, but do not evaluate the integral expression for the arc length around this parametric form. And they give you the equation. And you have to find alpha and beta, and you have to do something to it. Great. In this case, area can be really straightforward, so it's more frequent that area will be integrable by hand. But guess what we're going to do next? We're going to do arc length. And is arc length going to be very similar to what we did before? Yes. Point being, if you have to evaluate this, use your calculator if it's given to you. I very rarely will be mean enough to give you something that's not integrable by hand without a calculator. So let's say I asked you for this one right here. Did we just graph 3 sine 2 theta? Sure. We just graphed 3 sine 2 theta. So we have the formula there. If I wanted to find this area right here, the blue area, it's going to be 1/2 the integral from what to what? So what is f of theta here? Does it give us f of theta? Yeah, it's right there. What is f of theta? 3 sine 2 theta. And what do we do with that? Square it. D theta. What do I have not written in?
Your alpha.
Alpha and beta. Be very careful. Can someone tell me, raise your hand first, can someone tell me what the alpha and beta values are for this one? Anybody want to guess? What are you starting at and where are you ending at?
0.
T. Hands raised. T.
0 to pi over 2.
Oh, I like 0 to pi over 2. Who agrees with 0 to pi over 2? The way you think of it, if you can't see it, if you're starting here, where does this point start? It starts at 0, 0, right? What's the angle measure there? 0. And then if you travel along this, what's happening to theta? It's getting bigger, right? It's getting bigger, it's getting bigger. And what's this value right here? What theta value is right here? Pi over 4, right?
Yeah.
And theta's continuing positive, right? What's the R value doing? It's getting smaller, right? It's getting smaller, it's getting smaller. But what's the theta value here? You can think of it in terms of tangent lines. That's how I like to visualize it. What's the tangent line here? That's at 0. What's the tangent line here? Pi over 2. Like, what is the theta value there? Pi over 2? Are you okay with what I just explained there?
Wait, could you explain that again?
So the idea is, if I'm at this point, what's the theta value for this point?
Pi over 4.
And then it's the theta value for here, it's getting closer to pi over 2, closer to pi over 2. And then when it gets back to the origin, what's the theta value have to be for it to be back at the origin? Pi over 2. Because if I connect all the dots here, think of it this way. Let's zoom in a little bit. If I get rid of these lines, this might help. If this point right here is traveling along, theta value is getting bigger, right? It's getting bigger, it's getting bigger. It gets to what? What's right there? We think it's like pi over 4, right? What's the theta value doing as you go this way? It's getting what? The theta value is getting bigger. Remember, theta goes like this, right? The R value is getting smaller, but what's the theta value doing? Bigger. The theta value is getting bigger. And then what's straight up? It's at the origin, but it's straight up. So what's the theta value? Pi over 2. Now, this integral right here, you're like, oh man, I can do this. 0 to pi over 2. It's going to turn into 9, right? Of what? Sine squared 2 theta d theta. Is that something you want to do by hand?
Not really.
Do you remember doing those by hand? We did cosine squared. I think we did sine squared too.
Yeah, that was horrendous.
No, let's just pause, right? We're not super fan of this. It's not the best, right? I think it's parts, right? Is it parts? I think it's parts.
You do parts and eventually you find something that
Yeah,
looks
then you
like
do
it
the
on
sub
other
and then you double it and you're like, no.
Yeah.
But the point is, do you agree, or the question I want to ask you, do you agree that that right there is the area of that pedal?
Sure.
Are you okay with that? That could definitely be a multiple choice question on the BC exam. What is the integral that represents the area of one of these pedals? That's it. Okay.
Is it possible that they leave the constant under the integrand?
You mean like a plus C? What do you mean?
Like the 9 or something?
Maybe. They tend to clean it up a little bit. They like to write things.
That's what
You will generally see this. And the other thing that's a pain, because you've seen it before, because you've all taken the AB, is they'll give you like 4 other different expressions that look kind of the same. Generally speaking, it's my experience that they take the 9 out. Generally.
Could it also be like 1?
So when we do derivatives, dy dx, this should not look unfamiliar. dy dx is dy d theta and dx d theta. But if we are going to find dy d theta and dx d theta, we need y in terms of theta, and we need x in terms of theta. Well, do we have x in terms of r and cosine? Sure. And do we have y in terms of r and theta? Sure. So we need a function that dictates r. So for a curve r equals f theta, meaning they give us the curve, you can write x in terms of theta. So what's x going to be? F of theta cosine theta. And what's y going to be? F of theta sine theta. So in this case, find the slope of the curve y r equals 3 sine 2 theta at theta equals pi over 3. We use this right here. We use this right here. So what is r going to be? Let's look over to the right here. I think I just left it in here. Let me freeze for a sec so that you can figure it out. What do we know r equals? It tells us what r equals. So where do we plug that in? To r. So what does r equal? 3 sine 2 theta times what? Cosine theta. So what's y going to be? 3 sine 2 theta Sine theta. This is a trick question. Is there any simplification that can be done on any of these? Told you it was a trick question. Just say no. Just say no. I don't want you to like start multiplying sines together to get sin squared. Don't do that. Don't do that. Don't do that. Okay. So then you literally just apply this formula. What is, for example, dy d theta? What's dy d theta? 3 times what? Do you see what I mean?
Yeah.
So what do you get? 3 times, you have to use what rule? Product rule, the derivative of the first, so 2 cosine 2 theta sine theta plus sine 2 theta cosine theta, sorry. Cosine theta. And then what, do you see what I did there?
Yeah.
So there's your dy d theta. Great, you're really excited, aren't you? You're just so excited right now, yay. So you have your dy d theta. That's that. Great, so what else do you need to find out? So if you do dx d theta, what's that going to be? 3 times what? 2 cosine 2 theta? Cosine theta plus what? Sine 2 theta times negative sine theta. You with me? You're like, yay, oh, that's nice. So we have both of these things. So what does this look like when you write it out? Well, I did it over here for you, right? There are the two. We got it right. Excellent. We got it right. So if you wanted to state the slope, what did I write in there? Can someone say why with a smiley face right there? Why? If I wanted the slope, if I wanted dy, if I wanted to answer this question right here, at theta equals pi over 3, what do you now have to do? You have to plug pi over 3 into all of those. I'm not going to have us do that right now, but if you wanted to find the actual slope, it's y prime evaluated in pi over 3 over x prime evaluated in pi over 3, and you have to plug pi over 3 into all of these. Is it just busy work?
Yeah.
Yes, it's just busy work. It's just busy work. No, this is, I mean, that's just the chain. You've done that before. It's just, it gets ugly sometimes. It gets ugly sometimes. But you have a parachute that you can use when you're doing arc length integrals, because what did I tell you? A lot of the integrals are not integrable by hand. So what can you use? This look familiar? Oh, look, arc length is just going to be alpha to beta of integrating the Pythagorean theorem. Yay! Okay, did we already find dx d theta? Did we already find dy d theta? So what do you have to do to each of them? Square them. With the square root. And properly identify alpha. So if we wanted the arc length of one of those petals, right? Alpha to beta stays the same. What's alpha? 0. Beta is pi over 2, right? And then what do you have underneath? I think you can express it as bleh. Is that okay?
Yeah.
Because what does it look like? Ready?
Oh dear.
And even if you have a calculator, I know. Even if you have a calculator, so do we know what these are? Yeah. What is this? That's dy d theta and that's dx d theta. I think so, or vice versa. Yeah. And then you have to square them, right? Use the proper parentheses to not ignore those 3's. Even if you have a calculator, why is this a pain in the butt?
Because you can mess up.
You can mess up.
Oh my god! Oh my god, can you mess up putting those things in? Absolutely. Absolutely. So this is a little bit beyond the annoying algebra level that you'd see on the AP exam, because here's the thing. If they asked you this as a multiple choice question, they would be asking you what is the integral, not what is the value, because they don't want you to have to plug in as well. And the thing is, how many different ways can you mess up just writing that? All the ways. You can mess up all the ways, right? They want things that are less algebra intensive because they want to focus on testing you on the calculus, not just the algebra. So usually you'll get things cleaner than this, but if you can deal with this, can you deal with the AP exam questions? Absolutely. Absolutely. Again, generally speaking, and this is what you can take heart in, generally speaking, what's the hardest part about finding arc length in polar land? Finding the alpha and beta, exactly. Excellent. I think, if I got my timing correct,